Hey guys, so in this video we want to create some kind of splash animation, something like this, something you see often in commercials and so on. This is not a perfect render, it's a lot of flickering and the motion blur is a bit noisy and all that, but you get the idea. So how do we set something like this up? It's actually not too hard to get the setup. What is a bit tricky is this slow-mo effect, and that is something we want to look into in this video. So what we have here is a simple source sphere as usual, and we already applied a mountain to it so that we have a constantly changing shape. And then we use, of course, a flip source to create some points. So let's find something that makes sense. Maybe something like this. I mean, in production, of course, it would be higher, but for now, I think this is okay. So 002, let's make sure we put this on our controller. Okay, here it's 001. Actually, let's steal that. Let's use 001. Seems like a better approach. It's a bit, well, it's a bit too many. This is, I think, for rendering, that's a good idea, but for testing, it's a bit too high. Okay, great. So let's make sure that we actually have two of these sources, because what we want to do is really like in our video here, it's two streams coming from two sides and they just collide. And the interesting thing is that this happens automatically. We don't even have to do much as long as there is enough variation in the velocity, but that's something we will look in a second. So the second sphere I want to position somewhere else. Scale-wise, I think we're roughly in the scale of a Tommy, and I want to put them a bit of a diagonal to each other, something like this. So then we look from this angle. Yeah, something like this makes sense. And Tommy shows us this is roughly the scale we're talking about. And I think that makes sense. Cool. So let's merge them together. And first we want to make sure that our fluid simulation works in the first place. I put it into my standard setup here. Nothing fancy in it. A volume source, flip object and all that, gravity. So next I want to make sure that my calculation area is actually correct, so that we actually have the points inside of our volumes. So that looks good. We don't need that much on the top. There you go. And now if I run this, we should see the points falling down. And there you go. So they fall down. Great. So let's make sure we have a flip surface, a fluid surface it is, to make sure we can see the velocities. There you go. That's good. And now we want them to actually shoot at each other. And hopefully you know how to do this, because it's always the same. We just give them a start velocity. So this might be a little bit fiddly to do. I would do that with Vex in this case. And let's find the right direction. So here they are. So I would say -5, or actually -1. So it's in positive Z and it's in positive Y. So something like this. Let's see if that does anything. Yep, that's good. It's just not strong enough. So let's make sure that we multiply that with a speed. So let's call that, give that a speed channel, and maybe try 5. Keep in mind, of course, this is not a normalized vector right now, but it doesn't really matter as long as we have some speed. There you go. And I don't think that's too bad. Yeah, maybe a little bit higher. So we go 1.2 maybe for the height, and a bit more into -x. So I just copy that code. And for my second one, I just invert the whole thing. So what we actually could do here, now that I think about it, we could actually put that onto our own channel. So let's steal that for a second and put it into a comment so that we remember the numbers. And I create a vector channel. We call it direction, or dir. And what we have now is we can actually put that in here, those numbers that we found. And the cool thing about this is, if we copy the whole thing, we can actually reference the first one in this one, paste relative references, and we just invert it by just putting a minus in front. And we can actually already check this before the simulation by just showing the velocities. This goes in this direction and this goes in this direction. And since they're connected with an expression, it's actually the exact opposite direction of the first one. And let's see if they reach each other. Not fully. So let's make some adjustments here. Let's actually also lower the speed a little bit. Actually, we can connect those two as well. Copy parameter, paste relative references. There you go. And now let's try to tweak the numbers a little bit more. Oh, actually, the speed is important to keep it high, otherwise they don't hit each other. And yeah, they are colliding. It already does something, but we have to hit them perfectly. Yeah, that looks good. Okay, and now we have a splash. So now it looks like this. Now, before we move on, if you don't like that doing it manually, I think at the end of the video I will show you a way of calculating this automatically by just calculating the vector between those two spheres. But that will be at the end of the video as a little bonus. So for now, I think the manual approach is totally fine. So what we see is that it's working, but and we get a nice splash. But if we run this in more or less real time, you can see it's really fast, way too fast actually. Now what we can't do is we can't slow down the speed, because otherwise the water will never hit each other. This is actually the real speed that would happen. So what we can do to slow this down, to have this slow-mo effect, is we can actually use the scale time function. We cannot animate that one though, but we can at least lower it. So let's go down to maybe 0.1. And if you run this again, you can see it just the same thing happens, which you can see in a second, just much slower. And this is really a good way of doing slow-mo stuff if you know you want slow-mo the whole time. And you can see it works quite well. But what you can see here is it's kind of boring, the way the splash looks. It's very, perfect. Let's change the background color. And that is because all our points have the same speed. So let's fix that. And we do this by adding a little bit of a noise. We could do that directly in every node here, but I think it's easier to do this overall afterwards for both, because it's a bit easier this way. And we call this maybe V variant. And the idea here is that we change the speed of the points randomly. So it's actually quite simple. We know how to do this. We just multiply by a randomized number. And in our case, we could do that based on the point number. So let's see how this looks like. And you can see the different brightnesses now. The only problem with this potentially is that we slowed it down so much that now the curve will end up being too round and they will never reach in the center. So let's make sure that our random speed here, and you can already see that it creates a lot of variation, is we can fit range it. And actually, I think I do that. So we know that the maximum speed is 0 and the lowest speed is 0 and the fastest speed is 1. Yeah, and we want to adjust that to get a minimum speed and a maximum speed. So the fastest still should be, let's say, no, the fastest should be 1.3 and the slowest 1.6, something like that. So in other words, the minimum speed that a point can have of the original 5 is now multiplied by 0.6. Yeah, I think that's fine. And what you hopefully can see is that the splash should be way more interesting. I mean, what we can see is what the problem we have right now is there are not enough points, but you can already see that the splash is way more split up and has more complexity. Another thing we could do, which is maybe even better here, instead of using a rand, we could also use a noise, because currently we don't have a clear, pattern here. It's more broken up, but we don't have a pattern because there is no pattern in the randomizer. So let's use a noise. Currently the noise is too big, so let's multiply it. Let's maybe try 15. Yeah, this is better. So you can see now, from far away at least, that there is a pattern here that we can see. So it depends on your scale, of course. And of course, you can do all of this with VOPs as well. But for now, I think we leave it at that. And now the idea is that the different speeds are now basically in pockets in our stream here, which means that we should see that reflected in our splash. Okay, so I think our numbers were pretty good. The only thing I changed is I added a frame as an offset so that it's constantly changing our noise. And we always get a similar result. So one thing I would like to do is I would like to stop the stream after a certain point, maybe around here, so that we don't get constantly more water. And the easiest way of doing this is actually just with a switch. So we just switch at a certain point, basically we switch the water off. So F smaller than the number I want. So 25, for example, and after 25, it just turns it off and nothing comes out of it anymore. And it looks like this. Until frame 25, we have our sourcing, and then boop, it just stops. The result of that there's only a finite amount of water, and then it just stops. I think that's not too bad. Let's keep it at that. Let's actually make sure we have a bit more points, because the result will be much better. And here's the result, and you can see there's way more detail now, and that looks pretty nice. All right, cool. What we want to do is, as you can see now, the beginning is a bit boring, and then this is a bit too fast. So in other words, we will actually retime this. And this is something you see very often for something like effects like this. So you don't have a constant speed, but it changes the speed. The beginning is a bit too slow, and the end is actually too fast. For this to work, we will use the time warp in Houdini. It's actually the same as retime, as you can see. It's two words for the same note. And I want to show you how the easiest way I know to retime something like this. What I would do is I would change this to by frame. And basically what we have now, and you should always make sure that your input range is high enough. So maybe, I don't know, 400, it doesn't really matter. It's just so that it doesn't clamp the range. But what I would do is I set to frame, and then this is basically now working like a normal time shift. The cool thing about this is you can animate this. So what we want to do is we want to say, okay, up to this frame, let's say 43, this should be faster. So first of all, the first frame should be keyframed on the first frame. And then let's say we want to make sure that on frame, I don't know, 15, let's go in there with shift. On frame 15, what we want to see is already the result of frame 43. So we speed the whole thing up, and then our curve, press H, looks like this. So this, to be a normal speed, this should look like this. At frame 15, we should see frame 15, and the whole thing should be linear. So this would be a normal speed. By changing that number here to, let's say, 43, we already do a time warp. And we can, if we want, do this linear, or we can even animate it so that it speeds up or slows down. Then the next part is I want to have everything that happens later happen much slower. So let's say, when do we want to end? Let's say this is our last frame, 65, and this should stay for about 3 seconds. So let's go back to our time warp. So this is a speed up version. And then we say, from there, so 43 plus 75, roughly speaking, we end up at frame 110 or something. At frame 110, after 3 seconds, we want to have reached frame 60. And now let's adjust the curve a little bit so that it makes sense. And you can see now that first we speed it up and then we slow it down. Now, if we look through this and see what we get out of this, we should notice that it's not actually really working. Well, it does work. It seems to work, but then this horrible thing happens, and that is this flickering. The reason is that he currently does not interpolate the points. He just takes from the calculated points it already has. So make sure you turn on interpolate between input frames. Now let's see how this looks like. And it's actually even worse. It's kind of funky, it's kind of interesting. So it's fun to look at it, but it's really not what we wanted. So what's going on here? So the problem is that when I turn on the interpolation, unfortunately by default, the time warp uses the velocity. But it would be better to use the actual position in space because the velocity is constantly changing, especially when we read it out at different time points. So that's really not a good idea in our case here. This is mostly used for volumes. So let's turn this off. And now it doesn't look too bad, but sometimes it does this weird thing. So it got a bit better, but it's still problematic. Jesus. So the problem here is that when I turn this off, it uses the ID, which we know from POPs simulations already, to interpolate between the particles, which is great. Problem is, the flip simulation doesn't create ID attributes by default. We have to first go into the flip solver and the particle motion, and here add the ID attribute. I wish that would be a default, but I guess they don't want to create too much data, so we have to explicitly turn this on. So let's run this again and see how it looks like this time. And finally, we have what we want. And you can see that a time warp is often a really good approach, because now the beginning that we don't care that much about is pretty fast, and then it slows down to what we actually want. Now, doesn't that contradict my idea with the time scale time here? No, because you need to first have kind of a base speed. And so it was way too fast before. It is sometimes a good idea to combine a slow speed overall still with a time warp, because this just makes sure we have enough time to look at things, and the time warp is making sure we retime to exactly the speeds we want, which is usually changing over the time of the spot. Okay, so let me cache this out, because now it's a bit slow, and now it actually makes sense to cache this out with our ID attribute in it. And I use my preset here so that the naming is already good. And we only need 60 frames because this is what we use as our maximum in our time warp. So let me quickly cache this out, and I'll be back in a second. Now the next step, of course, would be to turn this into a geometry. So of course, a fluid surface node is what we need here. We make sure that we use our particle separation correctly. And then of course we can adjust it to what we need. But this is topic for another video. I don't want to go too deep into this kind of stuff because it takes a lot of time. To make this look good, I would have probably to adjust the numbers a little bit. But I just wanted to show you the overall workflow. Now, the thing is, as you can see, I usually cache my simulation before I turn it into a geometry, because this way I can always change my mind later without having to resimulate. And as you can see, even my time warp is happening after the simulation. I always try to keep as much data as possible from my cache and do all the other steps after the cache. So I could finish here. I think those are the most important things, really. But what I wanted to show you at the very end is a quick way of calculating this direction that we figured out by hand automatically, which is not really necessary, but some of you, I'm sure, would like to know how to do this. Everybody else can just stop here. So what we want to do is we want to have the direction between those two spheres. For this, we need the center of the spheres. So the easiest way of doing this is, I think, just pack the spheres first. And then use an add to make sure we only see the point. There it is. That's the first one. And we can do the same with the other one. And we end up with only 2 points, this one and this one up there. Now I create a point wrangle. The order doesn't really matter, but what I want to do is I want to calculate a vector I call direction. And this vector is the difference between the current position and from the first input, the position of the first and only point. So it looks like this. It's just a subtraction. And just to make sure, I normalize that and save it. And I already did that, so wait a second. So here on the eye, you can see I created a new attribute called dir. And if I click on it, I can actually activate a visualization for this. Unfortunately, by default, the visualization, I think, is set to color. So if you don't see a vector, make sure you turn it to marker and then turn the visualization on. There you go. And what we can see now is that the direction actually points in the wrong direction. And I made it a bit too long. If you want it to be shorter, you have to change the scale vectors. In my case, the length is exactly 1 because I normalized it. That was just so long because of my display options. So what you can see, it's actually in the wrong direction. So what can we do to invert that? Well, actually, we can just put a minus in front. There you go. Now it's inverted and it's pointing in this direction. Or we could just have changed the order of the subtraction. So this way we would have the same, as you can see. Now let's call this dir. And the idea really here is that we just steal that direction in our velocity calculation. So instead of using the channel here, I just read out from the first input the direction, that's the attribute I used, from the only and first point there is. So let's see if that actually worked by showing the velocities, and something went wrong. And the reason here, I think, is that this is currently not considered a vector. So let's quickly change this. So that looks better. It's the wrong direction. But for some reason, there is here some type conversion is happening. And I saw this before. Always check what comes out of it directly before you make any assumption, because the problem, interesting enough, is actually coming from this. So what I can do is I can actually force this to be a vector by putting it into vector and brackets. Let's try this first. And that actually worked. So keep in mind the velocity always shows the opposite direction of where it's actually aiming. So this is totally correct. So this worked. So let's steal this actually for our second vex code, and it does actually the exact same thing. We take the dir as the second input, and instead of calculating the vector ourselves or figuring it out ourselves, we in this case read it out, and then in this case we invert it as well. So theoretically, when we look through this, this should point in the opposite direction. So yeah, so this is how you would calculate the direction automatically. Let's quickly double check if that actually worked. And as you can see, that is correct. The only thing is, for some reason, because we didn't normalize it before, so we have to increase the speed a little bit to make up for it, because before our direction wasn't normalized. So let's try 8. And as you can see, that now works. Great. So I'm sure there was something you learned. Thank you very much. Keep in mind to cache this stuff out before you render it. And I hope this was helpful, and see you in another video. Cheers.